In this in this presentation, I'm going to talk about innovative solutions or next generation solutions that we're generating for power electronics and battery systems in electric vehicles with the help of generative design technology. I would like to start my presentation by talking about the vision, what we do at Diabatix and why we do so. We believe that smart algorithms can empower engineers to design beyond their imagination. This is very important at this moment. The reason is because the systems are getting complex and complex day by day. If you see the new complex and the complexity affects each other's performance. And because of that, it is very important to consider multiple aspects of the design. Not only that, going into the future, Industry 4.0 IoT are going to be inherent part of the design. And designing for all of these things, it is very important for design engineer to really design a system which not only accounts for all the scenarios, but also caters to different working conditions and different environments. At Diabatix, our founders really identify this type of need at the very early stage of the development. And that's where we start developing the smart algorithms and started putting these algorithms inside our platform called as Coldstream, which user can access it to achieve the highly efficient cooling designs. Our applications can range from automobile, aerospace, to energy, to any sector like data centers where thermal efficiency is extremely important, and it's the most vital thing for them. And because of the distinguishing factor that we have developed in this area, it has been identified by the two key partners in the CAD-CAE space, ANSYS and Hexagon, and currently we are technologically partnering with them. I hope this gives you a very good idea what type of smart algorithms we are developing and why we are developing them. But going forward, actually, I'm going to present to you how to implement or what or how Coldstream can really bring value to you. But in order to go there, we really need to understand what are the limitations which are coming from the current engineering design processes. The first important challenge in the engineering design process is basically there is lack of design exploration that happens at the very early stage of the design process. When the concepts are basically created and then they are taken forward with design and simulation exercises, these concepts are either driven by the manual expertise or by trial and error. We don't believe that that is a right approach to solve or go for the design product design approach, but rather a design exploration is essential to really identify what are the best candidates or what are the best solutions that you can generate as an initial starting point to later design to a detailed system design, which can definitely lead you to achieve the maximum performance that can be achieved from the product. If you consider electronic applications, power density is one of the important aspects, and conventional cooling designs do not really cater to the need where the increasing power density can be easily extrapolated with the current existing solutions. And because of that as well, design exploration is very important, which can not only provide great opportunities, but also help cost reductions. The third important aspect is manufacturing processes. This is very important because no matter how computationally efficient and clever systems we use, if the design is not manufacturable, the entire exercise is futile. And what we have also observed that the manufacturing processes sometimes drive the key constraints in the design process. Like, for example, manufacturing says that this is a constraint on a particular dimension, and you cannot put that dimension, so design process or design engineer cannot really account for that. So all of these things like manufacturing processes, manufacturability of the design, design entire process, looking for an objective like power density, all of these things are interlinked to one another. And achieving the best is finding the golden rule or golden solution for all of these solutions, and that's how the Coldstream is currently being devised. The way Coldstream is performing right now, it is based on 5 different dimensions. I will explain one by one dimensions, but with the help of these dimensions, it will be very clear at the end of the presentation that you can not only transform your product design technology, but also use these components in a very clever way to not only do design exploration very fast at the early design process, but at the same time use detailed design and subsequent generative design techniques to get the maximum out of the product design cycle. So the first important bucket that we're going to talk about is the generative design engine. This is a core technology inside Coldstream, and this is highly driven by the physics-driven techniques. When I say physics-driven techniques, the reason why I intentionally mention this thing is because this is not biased by the engineering judgment that comes from the human nature, or it doesn't have a trial and effect error coming from those type of approaches. Rather, generative design, since it is physics-driven, it mimics the physics what is happening in the process, and based upon that optimizes the design as per the need or as per the objective and constraints which are put there. So the design that comes out of this thing, it is highly effective in a sense that what objective users really want to achieve. We are going to talk about this in subsequent slides, but this is the most important piece and most core technology of Coldstream. Then the next bit that we have is basically a material database. In Coldstream, we have plenty of database which are used for the thermal cooling applications. Like we have n number of alloys and solid materials. We have multiple fluids. We have combinations of fluids like water, glycol, which is being used in various proportions and things like that. We have various interface materials and their properties. And because of this, the material database is very rich. User can use Coldstream very easily and start setting up his base case with the material database that we have already established. All of these things is also augmented by the third important module, which is manufacturing database. As I said, design for manufacturability is very, very important aspect of the product. If manufacturability is not guaranteed, the entire exercise of the product design is entirely futile. And because of that, we have also made sure that our processes not only account for the product design, but also for the manufacturability. And in order to make sure that exists, we have inbuilt developed a manufacturing database. I will list down in the future slides what all different capabilities or manufacturing processes that we have. But having said that, we can not only account for new technologies like 3D printing, but also conventional techniques like die casting, sheet metal forming, and so on. Then the next bit that we have is basically a shape generator. I would say this is also like one of the most critical or very important aspects of the Coldstream. The reason being, as I mentioned earlier, in the early stage of the product design, we need to have a fast concept evaluation process and exploration of design process as easily as possible and as efficiently as possible. And in order to do that thing, a computing system who is assessing the design space has to perform n number of iterations, n number of design explorations, n number of design variables to tackle and create new designs. And this has to be generated with a automatic technique of shape generation method, which is already established within Coldstream. We make use of BREP boundary representation based CAD generation techniques as well as implicit techniques, and we generate complex shapes ranging from simple pin designs to complex shapes like gyroid, lilinoid, these type of TPMS structures, which allow us to basically explore the entire design space with the help of standard designs. And that's why we call this thing as a shape generator, which is also a very important piece of the Coldstream. And the next bit that we have here is basically a simulation engine. What this thing allows you to do is basically this is basically a standalone simulation capability that user can use either for doing some simulations or doing design verifications generated by the Coldstream. Now, with the help of these 5 buckets or the 5 pieces of 5 dimensions, we believe that we now account or cater to a newly transformative generative design product design technique, which I would like to discuss on the next slide. On this slide, I'm showcasing what is the traditional technique of the product design that we have currently established. So it begins with a concept. This concept would come from the human expertise, or let's say trial and error concept, which later then converted into the design and then iterated with design modification in conjunction with simulation. A simulation basically mimics how it is going to functionally operate in the operating conditions, and then basically design modifications and then simulation iterations continue to go on. Once the design matures and satisfies the constraints, it goes into testing and validation, and then the final design is created. So a design space which looks like this at the start as a concept, which can later mature to a design like this, which is shown on the right hand side. Now, looking at this, considering the conventional manufacturing processes as well as the conventional or traditional design processes, most of the designs which come out of this type of exercises, they are quite regular in a sense that they may not be able to extract the maximum thermal efficiency out of the expected performance that the customer is really looking for. And if this thing doesn't work out, then the entire process basically repeats again and again. What we're doing at Diabatix is that we are developing tool sets or modules which basically transform this type of workflow into a generative design workflow. And what I mean by that thing is something like this. What we do at Diabatix is we provide a range of modules. It starts with a defining concept. In this case, the concept is designed only by defining the objective or the constraints, what exactly user wants to achieve in terms of quantifying the numbers. For example, like user wants to minimize the temperature at certain area. User wants to minimize temperature spread or temperature unit. He wants to maintain a temperature uniformity at certain area. It begins with a concept like this. User can define a design space. A design space is really to explore for computing systems how far or what design should lie inside a design space, so that it can vary the design or it can generate different shapes, as I explained in the previous slide, as much as possible, constraining within that design space. Once this is established, we make sure that our fast concept generation algorithms generate n number of ideas within short span of time. Typically, we generate 100 different ideas within few hours, and that basically is evaluated very fast in terms of objective and constraints which are defined in the conceptual definition level. At the end of the exercise, a user can basically see a performance curve, like design performance value with respect to number of designs performed, and based upon that, user can also see which are feasible and non-feasible designs in terms of manufacturing. Now, once we have this thing, user can then basically transform all of this exercise into an exercise called as going from concept to final design phase, where user can pick basically, let's say, 5 different ideas or even more. But then by using, let's say, clever techniques or using Six Sigma techniques, one can filter out the concept which may not be feasible or may not be viable, and then take up filtered ideas or funneled ideas into the next step. The next step is basically using the concept designs and transforming them into detailed designs, where a thorough analysis and thorough development of the product can be done based upon the originally developed concept. So this concept can transform into a detailed design, something that would be much closer to the real application or real expected outcome that user is expecting. So that way, user can do maybe 2 or 3 different ideas and can transform into the detailed design. And essentially, this then can be later transformed into a testing validation depending upon the performance evaluation done on the detailed design. So this is the way how actually we are transforming currently the concept design into a final design. And basically, the expected output at the end of this exercise is not a design that looks very much like this above, which is very conventional in terms of designing and manufacturing, but something that caters to the to maximizing the performance at the same time it is cost effective. I will give you one demo later where I will show you how we are designing battery cool plate, but this is the entire idea actually with which we are driving our developments. Now in Coldstream, it is very important that we already have uh, a concept generation module, and there is a specific reason why we have developed this module. If we see the early stage of the design process, this is a place where there is scope to develop n number of ideas, but we also see that there is lack of capability in the market where there are very less tools which can really generate n number of concepts at very ease, and not only that, they can couple those n number of concepts with a real engine which can basically evaluate those performances. In terms of flow solver and thermal efficiency, I believe Coldstream could be the only platform which allows user to generate a number of concepts. Now, why do we do that thing? The first thing, as I explained, we need to make sure that we need to explore or we have capability to explore the design space as easily as possible. And by doing design space exploration, we are actually trying to really identify how the performance curve really looks like when the design variables are tuned or varied with respect to different variables. Now, one can generate these concepts just by using trial or error or engineering judgment. But the next step where the Coldstream really makes a difference is basically achieving the maximum thermal performance, in the sense that going from target 1 to target 2 and achieving a real global optimum for that particular design process. This is very important aspect of the Coldstream. The reason is because a user can really generate concept 1, concept 2, and start from there and evolve the design. But it may happen that user may get stuck in the local minima and not get the global minima. So, for example, if you consider concept 1, user can begin with concept 1, but it may happen that his solution may converge to a local minimum. And this is the thing that we really want to avoid, and that's why the Coldstream has different modules which allow not only the concept generation and thereby design exploration, but at the same time, after concept generation, it pushes the design to the next level where you can achieve, or you can go from target 1 to target 2 and achieve the global minimum. I hope this gives you a really good idea of what different types of models we are developing, but at the same time, in conjunction or combining different modules to one another, user can really have a perfect design cycle. What I mean by that thing is, a first module could be a fast concept generation module where user can use this module at the very early stage of the design process to really identify what concept would serve as a starting point that will basically serve as a really good starting point for the next detailed design. So so Coldstream can really give you like thousands of different ideas, which can be then funneled later and can be taken into a detailed design, like a generative design, and in which actually user can set up a detailed case and try to achieve the best performing thermal design out of it. Now, user can also try to tweak multiple aspects of the design process, in the sense that user can do less accurate design exploration first, then highly accurate design exploration later, and then get to this phase. But that's where we say that user has a will to combine multiple aspects of or multiple modules all together to come up with a perfect design cycle that is suitable for his product development. And at the end of the exercise, after developing, let's say, a highly efficient thermal design, user can then go to thermal analysis, where he can explore different concepts, try to compare various reference simulations to one another, and try to make sure that the design that is coming out is really a global minima and not the local minima in this stage. I hope this gives you a really good idea, actually, how different modules can really help to build a perfect design cycle. And by doing this thing, it really explores or gives opportunity for user to really create a limitless design design options. This gives user a limitless design freedom, and this is very important in terms of generating a number of designs or a number of concepts, because different manufacturing processes, different objective, different settings can converge to different designs. But having said that, this different manufacturing process can really govern actually how a design is really going to play out or can be manufactured in the real application point of view. As we have seen in the recent times, 3D printing has emerged as one of the key technology which provides limitless design freedom as well. But at Coldstream or at Diabatix, we have vision where we're not only accounting for advanced techniques of 3D printing, but we are also accounting for traditional or conventional manufacturing processes like machining, screwing, stamping, or die casting. By doing that thing, we also address to all the other sectors, for example, like automobile, where manufacturing a component in large quantity is very much important, at the same time getting the thermal efficiency. In that case, maybe a low batch manufacturing with 3D printing may not be an ideal suitable candidate in this case, but die casting or sheet metal forming could be an ideal candidate. On the right hand side, this is just a one example that I wanted to show you, which we did for an automobile OEM last year. They especially asked for a highly efficient design, which we created for the electronic appliances, but they also asked us to create a design with die casting manufacturing processes, and our portion was able to deliver a highly efficient design with the help of this technology. I hope this is a really good overview what Coldstream can really do, how Coldstream can really transform your product design cycle. Going forward, I would like to present you a simple case study. And in this case study, we'll be talking about a battery cooling cold bed design for an electric vehicle application. As I mentioned earlier, our applications are getting complex and complex day by day. And because of that, since there are multiple subsystems, since there are multiple objectives and targets which need to be satisfied for a given design to be manufactured, it becomes a burdensome for design engineer to make sure that all of the different aspects of the design are correctly captured. In terms of like EV battery cooling cold plate for this case study, we took 5 different challenges in order to come up with a cool plate. This first challenge was basically to maintain low global temperature. What it means by that, at any XYZ point in the cold plate, temperature should not exceed beyond a certain threshold temperature. The second challenge was basically thermal uniformity. In this case, the temperature of the cold plate should be as uniform as possible in any XYZ location, and comparing all over the cold plate locations. The third challenge was the pressure drop minimization objective, but we put a hard target on the pressure drop, and we mentioned that the design should not exceed a pressure drop above a threshold value. And then the manufacturability. For this case, we just made sure that the manufacturability is done with the sheet metal forming. And then we also try to limit the weight of the cold plate that should not exceed a particular threshold value. Now, if you consider all of these requirements, accounting them at one single time in one single setup, it's not that easy with the conventional manufacturing process. But with generative design, we can not only account for all of these constraints and objectives, but you can even tune it further. You can add even more constraints and really define your case for the manufacturability that you are looking for. I will explain a little bit in details what this case is about, and how all of these challenges basically translate into a quantifiable numbers. So this is a case study that depicts actually what exactly was the case. So here on the left-hand side top picture, you are seeing the cold plate. There is an inlet here. There is an outlet here. The cold plate contains a fluid volume here, and there is a design space which is subset of the fluid design. Ideally, this should be spanning from here to here. So ideally, with the sheet metal forming, portion should be able to create structures in such a way that flow should be guided from inlet to outlet in such a way that the heat source, which is applied at the bottom of this cold plate, should translate into quantifiable objectives which should be made by the cold stream. For this case, we used water 50% and glycol 50% as a coolant. As I mentioned earlier, we have a wide range of coolants and fluid-based properties for your thermal applications. We used one of them as 50% water glycol coolant. And on this bottom heat source plate, we applied 800 watt as a cooling or the heat input. In terms of objective, we defined minimum peak temperature as an objective, which essentially translated into not exceeding a temperature above 35 C or 35 centigrade. Then maximum thermal uniformity, which essentially translated into a temperature uniformity of plus minus 5 degrees centigrade, not more than. So any point so all of the points on the cold plate should not be exceeding more than 5-degree temperature than the average temperature in the cold plate. Then we also put some constraints in terms of pressure loss and essentially, as I mentioned, the temperature uniformity criteria. In terms of pressure loss, we put that pressure should not exceed 5,500 Pascal. And then, as I mentioned, the manufacturability was again the sheet metal form. Now, with these constraints and objectives, we set up the model, and Coldstream gave us an output, which I believe I can show you and compare and present you the comparative results in the next few slides. First of all, I would like to show you what Coldstream really produced. So this is a design that Coldstream produced in this design space. Now, this looks a highly flow-driven design or highly flow-friendly design. And in the next slide, I will show you how it compares with the conventional design as well. But looking at the design, manufacturing or coming up such a design completely through the manual experience is highly unlikely. And by exploring the generative design techniques and making use of highly performing computing methods, we can allow user to basically come up with the designs which are basically provided by optimization tools like Coldstream. Now, having said that, let's try to go on the next slide and try to compare various designs that we created in order to compare it with one another. The first design we created the same design space. Only thing is that this could be you can call this as a conventional design, where inlet and outlet are connected with a maximum flow path in terms of a zigzag channel. Then second conventional design that we created was made up of the dimple shapes. These are spanned between this area, and inlets and outlets are connected by the passages which are in between these dimples. And third design that we just talked about was given by Coldstream, which is very much flow-friendly design. Now, if you compare the performances in terms of temperature and how it ranges. So first of all, the temperature values, if you consider various plots that I'm showing on this slide, the generative design reached the least amount of max temperature as per given max temperature criteria or max peak criteria. It reached only 31 C, but rest of the designs reached more than 31 C. So here, the Coldstream was able to constrain the design to limit it to 31 C. Then We also can see that the range of these points within this delta T space are very much constrained when it comes to generative generative design. By means of that, the spread or thermal uniformity of the objective which we applied for generating this design has also worked extremely well in comparison to the other designs. So in case of dimple design, the spread goes from 21 to 32, but in comparison to that, in case of generative design, it hardly goes from, let's say, 24 or 25 to maybe 31. So that's the way how a generative design can really help out to limit the performance and achieve the best objective possible. In terms of pressure drop, you can also see that in this graph, the S-shape design and the generative design are highly comparable when it comes to the temperature. But when it comes to pressure values, the S-shape design turns out to be highly inefficient design, and the pressure loss is almost 4 times than the expected target value that we want to set. So here it was 5.5 kilopascal. The ranging pressure drop in S-shape channel was about 23 kilopascal, which is highly inefficient design in terms of pressure drop. Other designs like dimple designs turned out to be pressure drop efficient, but they are not efficient in terms of like the temperature expectation that we have. But if you see the generative design, it not only meets the temperature-based criteria or temperature-based expectations, but also meets the pressure loss constraints. And this is the way what I mean by generating clever and using smart algorithms to generate designs which can not only excel in terms of taking design to the next level, but also user can achieve maximum thermal efficiency and performance with the help of such techniques. This is just a summary of the comparative study. Based on what we just discussed, the S-shape design is good in peak temperature and uniformity, but fails in pressure drop. The dimple design fails in peak temperature and uniformity, but fails in pressure drop. But the highly efficient design that was created by Coldstream meets all of the expectations, like maintaining peak temperature, uniformity, and pressure drop. You can also go to the to our website where we have a number of papers listed and try to see which application or what type of capability can suit your application the best. These papers are available for free. Please go ahead and try to explore how Coldstream can really help you out with your product design aspect. And if you have any interesting ideas, interesting cases to work with, feel free to reach out to us. I would like to also show you some of the important capabilities that Coldstream has in terms of few of the applications that we can really do. So we can cover broad range of applications, starting from air-cooled electronics, liquid-cooled electronics. I just show you battery cooling applications. Then we can also do flow optimization in order to maintain uniform flow at the outlet, like manifold designs and things like that. We can also do e-motor cooling or casing design. We are also working in electronics or CPU, GPU cooling and various aspects of this type of applications. And that makes us like very versatile Coldstream as a product for the product design opportunity. Now, I hope this gives you a very good idea, first of all, how Coldstream can really help you out, and then the case study to showcase what outputs Coldstream can really generate. Now, I would like to give a very short video which will tell you or which will show you how Coldstream interface looks like, how user-friendly it is in terms of setting up the model and looking at the results, and how easy it is to basically create new designs with the help of that. So here it is showcasing all the different geometries which are uploaded. These are basically step files, and you can easily set up the input, inlet, outlet boundary conditions. At the same time, you can also set up like extra constraints on top of that, like temperature constraints, temperature uniformity constraints, max temperature constraints. We have a wide range of applications available. Now, with the help of that, you can do the simulations and Coldstream can generate a design that looks like this. And then that basically can transform into a design that can maintain the thermal uniformity as much as possible. So here you can see a design that was generated by Coldstream. Then the streamlines, which are basically showing how a fluid can flow, and then basically different different contour plots representing how thermal performance can be maximized for this type of applications. Yeah, I hope this was an overview session to give a really good idea how Coldstream really works, what are the capabilities of Coldstream, and how you can use it for your next generation product design cycles. So if you are interested to design a highly efficient cooling designs, please feel free to visit Coldstream application and contact our sales team. We are more than happy to accommodate and help you out with your design cases, and help you out with setting up the cases and making sure that you get the desired result that you're looking for from using Coldstream and generative design. So thank you very much for this listening. And if there are questions, I'm happy to answer them. Thank you.
Okay, yeah, Yogesh, thank you so much. I think we have some questions which possibly we got it over chat. So maybe Vidya or somebody, please, others, you can have the questions.
Yeah, Yogesh, good morning to you. This is Ramesha.
Hi, Ramesha.
First of all, thank you for this insightful presentation. I have a question this: can the Coldstream integrate with existing CAE tools?
Yeah, it's a very good question. Currently, we have capability to input step files. So you can export step files from any of the platform. It doesn't matter. It can be Autodesk Inventor, it can be SolidWorks, or any other CAD package. So from input point of view, we can have capability to import any file format in the form of step file. In the form of doing simulations, currently we already have established a connectivity to ANSYS, and when we do generative design, Coldstream also exports input decks for ANSYS actually, so you can also take advantage of those exported outputs to do analysis and simulation inside ANSYS. But we are also exploring and integrating these with other CAD packages and CAE packages in the future, and that will come in the near future. Most probably, some of the applications will also come in 2025.
Yeah, thanks, Yogesh. And another question I have, if you don't mind, like this platform, the Coldstream platform, does it give any real-time feedback or design suggestions to the engineers?
Actually, that's a very good and interesting question. So first thing that Coldstream really gives you is, maybe I can quickly go back to my presentation if you can really see. During the execution of some of the cases, user can really see a performance curve being generated in real time. As in, let's say, for example, Coldstream evaluates, let's say, 10 different concepts. And the concept generation is still in progress. User may be able to see 10 different points which are representing how the performance curve looks like with different design variables. So in terms of real time seeing how the performance curve is really looking like, that is something that Coldstream can really do, or the capabilities are already there. But at the same time, a user can also download the already existing designs while the simulation is already running. So we have capability to export the generated designs in the form of step files or STL files or 3MF files, and user can simply download those files and start working with those files while the design exploration or generated design is still in execution.
Yeah, thank you, Yogesh.
Cheers.
Hello.
Yes.
Yeah, Yogesh, I have one question. See, generally for battery packs, we have three different type of cooling systems, right? Like air cooling, forced air cooling, and liquid cooling.
Yeah.
So if we propose our design, what you will suggest, what type of cooling system should be used for that?
What we can basically do is in cold stream we have capability to do air cooled forced convection or natural convection, at the same time liquid cool uh, capabilities of cooling applications. What we can do is we can help you out to set up conditions or cases in all of these three different formats, and cold stream can also do comparative study in between them when the case execution is really happening. So if you set up a platform like that, a case setup like that on the platform, you can get already a comparative study and maybe even able to explore the best candidate out of those three conditions.
Okay. Thank you.
Yeah.
Yogesh, we have one question on the chat box from Nitin Kumar.
Yeah.
He wants to know, what is the output format for the solution? Is it step file?
Yes. So we have three type of output formats. First of all, we provide step file, which can go easily into your PLM systems. We also export STL files if you want to do 3D printing and things like that. That is also possible. We also export 3MF file format that is more efficient or like more versatile kind of STL format. But these are the three formats that we export at this moment.
So Yogesh, I have the question. I'm Nitin Kumar. Thank you for this wonderful presentation. I have a question. You mentioned that the output is in the step format, and initial level you also mentioned that you have some kind of a manufacturing kind of a understanding. I mean the design for manufacturing, right?
Yeah.
So this solution, what is developed, let's say this solution is for die casting, yeah?
Yeah.
And your shapes are generated. I
Right.
mean, do I need to take this step means do you also give a manufacturing I mean a manufacturable kind of a step file, or do we need to take it to the CAD and again perform the DFM design for manufacturing?
No, not at all. So in case of code stream, all I need to do is specify what is your design space. So design space will basically tell code stream how a design can be varied within the space. Then in code stream, we have a separate module called as setting up the manufacturing settings. For die casting, let's say you can define like fillet radii, inner fillet, outer fillet, then what should be a draft angle, what should be the height of the islands. You can define those parameters and CodeStream will generate manufacturer designs for you. You don't have to do anything from your side. You can just simply download design and start manufacturing. So that level of understanding we have already built in CodeStream. CodeStream will make sure that the outputs that it exports are always manufacturable. If the designs are not manufacturable, it will specifically mention on the performance curve that this design is not manufacturable, or in some cases it will also avoid completely generating these type of designs.
Okay, great. I mean, it would be really great. I mean, in the future, there is like a kind of a manufacturing drawing itself, which can be shared with the vendor.
Okay, okay. I think what Nitin, I can suggest you is we already have those type of things available on our documentation page. We recommend you, maybe you can contact our sales team and we can help you out to guide with all sort of questions that you have in terms of manufacturability and even get you on position to try it out.
Thank you very much.
Yeah.
I have a question. How does Coldstream balance simulation accuracy with computational speed?
Okay, yeah, that very interesting and very important question. I think accuracy is very important aspect when it comes to doing physics-based simulations. What we have developed within CodeStream is, as I mentioned, we have fast concept generation modules, and then detailed modules. Typically, we use highly performing computing clusters behind the scenes, behind this cloud platform to all of our computations. In the early stage of the design process, in order to do very fast computations, we typically use lesser accurate but highly productive design iterations. so that user can really get a good feel of how the performance curve basically looks like when ColdStream really explores the design. And then actually when the concept basically mature, then ColdStream basically uses highly detailed, highly refined mesh models and computational techniques on highly computing clusters, basically to come up with a global minima. Actually, on this case, by allocating highly parallelized more number of CPU GPU clusters to solve the problem. So this happens dynamically behind the scenes. User can do settings for that thing as well, but we have wide range of settings in order to help user to accommodate different type of computing solutions with different accuracies at different stages of the design process. Hope this answers your question.
Thank you.
Yeah.
Hi, Yogesh.
Yeah.
It's Tabish here. Thanks so much for this technical presentation. It was very insightful. So I have a couple of questions. One will be the extension of the Manu question. Suppose you have a very complex computational system. Will it be able to handle all these type of requirement for the computational resources, or otherwise you need any high computational resources to carry out this thermal type of simulation?
Yeah, it's a very good question. You don't need to have any computational system available at your disposal. Everything will happen actually on the cloud remotely, and you don't have to really do anything locally. So ColdStream comes with a highly computing cluster based backend behind the scenes, and all the computations basically happen on the cluster. So you don't need any hardware. All you need is basically a design concept and maybe the input files like step file and boundary condition file, and that should be sufficiently enough for you to get a design.
Thank you. One more question. This ColdStream pricing model I wanted to understand. Is it a subscription based or per simulation based pricing?
Right now, this is a subscription-based model that we have. However, some of the cases, if customers are willing to do simulation-based subscription or simulation-based simulation-based execution, then we also allow that thing to happen. But right now, majorly it is subscription-based model that we have implemented.
Thank you.
Yogesh, I have one question. So does ColdStream support multi-physics simulations, including conjugate heat transfer and fluid structure interactions?
Yeah, so right now we have conjugate heat transfer already embedded. The physics related to that is there. So any problem related to heat transfer plus fluid flow can be easily solved. Regarding fluid structure interaction, currently we are building this type of capabilities. Means we don't have structural part yet fully established, but this is something that is going to come in the future. But having said that, CHT or conjugate heat transfer is something that is readily available at this moment.
Okay, great. Thanks for that. I have one question on the chat box.
Yeah.
So the person is asking, Manu is asking, does the platform allow user-defined material properties and custom heat transfer models?
Yes. So as far as materials are concerned, user can define as many materials as complex materials possible. We can have also temperature dependent material properties defined on the platform. So no problem at all regarding that. In terms of defining user-defined heat source models, right now we have limited capability, but having said that, it doesn't stop you from submitting like most complex cases on the platform. We are covering wide range of applications in terms of input that you can provide it to ColdStream, at the same time the objective and constraint that you can put on ColdStream. So yes, it is very much possible, and yeah, if you want to know more, just feel free to reach out to our research team.
Yeah, thanks, Yogesh. Hope Manu, Yogesh has answered your question. The next question we have is, has ColdStream been validated against experimental data? If so, how close are the simulation results to real-world measurements?
Yeah, so we have plenty of cases where cold stream data has been validated. What we have seen typically, the error was up to 6% on an average. In terms of simulations and experiments, there are always gap, but this is very good performance in terms of the accuracy that Coldstream has already produced. We always make sure that the meshes or the convergence that happens during these computation techniques are very critical and seriously taken upon, so that we make sure that the physics and all other physical phenomena are correctly captured. So in terms of accuracy, yes, as I said, on an average 6% within the experimental value, that's what we have also achieved. But also, if you go on YouTube, there's a very interesting video that we published in the recent times, where we wanted to design a highly efficient cooling system for GPU coolers, and it basically outperformed every single design that was possibly made up to date by conventional or any advanced systems so far. So Diabatix's design basically stood out as the best design so far. It reached out the expected values efficiently. Maybe if possible, we can share even a link. You can go to YouTube and see that video as well. So to answer the question is yes, it is validated. Plus, we also have some data readily available on YouTube, which you can also check it out.
Okay, great. Thank you. We also want to understand what kind of onboarding and technical support Coldstream provides to new users.
Yeah, okay, that's a very good question. So regarding onboarding, actually, the first meeting actually happens with the sales team, and basically we make sure that we have proper NDA and written acceptance documentation properly set up. Once that is done, we arrange an onboarding session where we give access to the Coldstream platform. User can take up to 2 weeks to really get familiarized with the platform. Till that time, your subscription really doesn't start. It's a free time for you to really explore how Coldstream is actually, how the platform is, how user friendly it is. Once the subscription starts, we provide a full training how Coldstream should be used, how all features basically are listed on the platform, and how to use them. And once that is done, we also set up a weekly sync meeting to make sure that your progress is happening, and we can help you in the best possible way to not only cater to your question, but also to achieve the best performance that you are looking for. So that's the thing. We also have like 14-day trial period if you really want to get hands on it. It has limited capabilities, but it will give you a really good idea how the Coldstream platform really works. So if you are really interested, you can also go ahead with the trial program. But then again, we also have some subscription programs as I mentioned earlier.
Right. Thanks, Yogesh. The next question we have is, what level of automation does Coldstream provide for optimizing cold plate designs?
Yeah, very important question. I wanted to highlight this thing earlier as well. The important or the inputs which are required to set up the Coldstream case are very simple in a sense that all you need is basically a geometry file. It could be a state file in the form of what geometry or what shape you really want to optimize, and then whatever boundary conditions really want to put in on the case. The rest of the things like automation, in a sense that hitting the submit button and starting the generative design process to delivering the entire design is completely automated. User doesn't have to really worry about anything in between. User can check what is happening in between, like he can check the progresses, like for example this performance curve that you are seeing on the screen. User can check, okay, 10 designs are generated, what does 10 designs look like. User can download the designs, but really from automation point of view, user really doesn't have to worry about anything. apart from submitting the case on the platform. So everything is taken care in the backend, and a user can simply expect a step file as a design file coming out of the entire exercise.
Yogesh, one more question.
Yeah.
So just wanted to understand, the Coldstream does support your phase change cooling system or two-phase flow cooling systems?
Yes. So yes, Coldstream supports phase change systems, phase change materials, as well as two-phase fluid flows. So that is also totally possible to simulate in or to design it for in Coldstream.
Okay, we have one more question on the chat box. How much time does it take to arrive at a design from clicking the submit button? Is it hours or days?
There are different modules that we have. So if I maybe here. So if you see the fast concept generation process, our estimation time is generating 100 designs in less than 8 hours, considering the fastest technique that is available. Then we have also mid-range computational techniques where it can generate again hundreds of designs in maybe 2 days or 3 days, and depending upon that, if you choose the detailed design is a highly complex and a very refined model. So depending upon the problem that we have set up, we have seen on an average it takes about 10 days to 2 weeks of time to get the design out of the question.
Okay, thank you. Do we have any more questions at all?
Yeah, just one more question. Hi, this is Jagan from Chennai.
Hi.
So the way I understand how Coldstream work is, you just import a model with inlet and outlet spout positions and the available space. The Coldstream will generate the optimal flow path, right? So this
Yes.
works with one fluid. Is that right? There is only one fluid in this operation.
This
Okay.
it can have multiple fluids as well. It's possible. Yeah.
Okay. So suppose we are working with radiators. So radiators will have tube and fin like structures where there will be internal fluid as coolant and the external will be the air source. Okay.
Yeah.
So can Coldstream, if say if I already have a CAD model for a radiator which consists of tubes and fins, can Coldstream further optimize the tubes and fins to get a better profile or better heat transfer area?
Yes. Coldstream can do that thing. It can handle multiple fluids as well. Yes.
Sure. Thanks again.
Yeah.
Hello.
Yeah.
I am Madhavan from SM Auto Engineering. Can it be used for pressed coolant plates?
So we use this thing for almost every single thermal application processes. So if your problem statement is about making the solution thermally efficient, yes, it is possible to do that thing. What I can suggest is maybe get in touch with sales team, and we can get you maybe even trial period to see how we can help you to set up your problem and provide a solution with that.
No, what I mean is that cooling path is generated by pressing two plates. Then they are joined actually.
Okay. So you mean the manufacturing technique is different?
Yeah. You are talking about the only die casting you have been touching.
Okay. So for that, I will have to maybe check with the R&D team from Diabatix. We have previously done such a custom case for one of our clients, but I will have to get back on this with you.
Yeah. Maybe Yogesh, if I can briefly step in here. So it is actually perfectly possible. So if I understand your question correctly, it sounds very much like our typical battery cold plates, the way they are manufactured, where you have a press plate that is then welded against another very thin sheet metal plate. If that's the case, it perfectly it will perfectly work.
Okay. Okay. Thank you.
So it's basically what you see on the current slide on your screen. The top right example is basically one of the two plates that you see then. And so, but
Okay.
it's perfectly possible then to weld them, to close them via welding afterwards, and also those the requirements with respect to the minimal width for your welding line, or how shall I call it? Also those parameters can be taken into account during the design process.
Okay.
Any more questions? Yeah, if you have more questions, please feel to write to us on events@citadel.com. I've just put the email address in the chat box. But if you have any more questions, Yogesh will be happy to answer. And Levin is around as well now. So yeah, please shoot your questions if you have any more. We have 5 more minutes to go. It doesn't look like we have more questions, but please do write to us. Thank you so much for your participation today. Thank you, Yogesh. Thanks, Levin and Vijay. It was a wonderful presentation.
Yeah,
Thank you.
Our pleasure.
Yeah.
Thank you, everyone. And yeah, please.
And so,
yeah, go ahead, William.
yeah, it's good to say the same thing. So for everyone who is triggered after this presentation to further explore this, please reach out to either us or directly to our partner Xitadel. We're more than happy to help you get started with the platform and to help you, improve your design process as you have it in place at this moment.
Yes. So we will send you a Thanksgiving email, and we will also request for a small demonstration or the further engagement on one-to-one basis level to all the participants. And if anybody is interested, then we can schedule a one-to-one meeting based on their availability.
Thanks, Vijay.
Okay.
Okay.
Thank you so much.
Have a nice day to everyone.
Thank you.
Thank you, Levin. Thanks,
Thank
Yogesh.
you.
Yeah.
Bye-bye.
Bye-bye.
Bye.